Okay.
Yeah, I can't see anything yet.
Okay, it says go live at this point.
Yeah, it's live. I can't see anything yet.
It's live.
Perfect.
All right. So yeah, Simon, I think we can start.
Uh-huh.
Let me do a short intro. So hello everyone. Thank you for being part of this talk. It's part of Unikraft Summer of Code, and today we have Simon. He's the main technical person behind Unikraft to give an intro of debugging and tracing in Unikraft. It's actually very well tied to the third session in Unikraft Summer of Code. This is a public talk. We are very happy and thrilled to have it streamed live to everyone who's available, and it will also be available to anyone to check afterwards. That being said, Timon, thank you so much for being part of this, and you have the mic.
Thanks a lot, Rasan. So yeah, I will talk today about debugging and tracing in Unikraft, which is, I think, as soon as you do some development with Unikraft, something really important. This means also that probably with the session that you're going to take then, there will be some repetition, but I think it's not a bad thing necessarily, because this is kind of the standard tool set you should be able to rule, let's say, more or less when you start developing things for Unikraft. Okay, in this talk, I will go over actually 5 points. First, we will talk about the print system. There's a print system actually that Unikraft provides and makes you, in some situations, easier to debug things with printing. Then we will talk about assertions that are provided. The third point is about GDB using the GNU debugger. We will also talk about trace points. And at last, I will give you an outlook of even more features and tools that we're currently working on and trying to integrate into Unikraft upstream that makes, even in certain aspects, like if you further want to performance improve something, the life easier. Okay, let's start with the print system. So you probably know it under the printf debugging, the poor man debugging, or however you call it. Actually, most of these functionality is provided by the UK debug library. Probably you saw it already when you do a craft or a make menu config. The Unikraft one actually had one basic idea behind that it wants to place, actually we want to place the code only into the final binary when it was enabled at compile time, meaning that you configured it to be there, and then it should be also in the final binary. And if you unconfigure it, it should disappear completely and shouldn't affect any of your performance properties. So these configuration options you find so if you do craft menu config or make menu config under library configuration and UK debug and tracing. We have two message types. One we call kernel messages, which is kind of close what you maybe know from the Linux kernel. When you do kernel module programming or something like that, you probably saw something similar. We have also 4 different levels of messages. And then we have debug messages, which are intended to help you while you're developing something, but you can also leave them in your code for, let's say, a bug is found later in a later point of time, and you want to switch on that old development view again, and you see the original debug messages that may help you doing some state. I hear some noise in there. I think someone had enabled the microphone.
I muted them.
Okay, perfect. Under the hood, really short, so that you just know how the principle works. Each platform library that you compile your code with is defining a UK-cout and a UK-cout D function, which are the console output functions for the kernel, and the debug message. The thing is that the driver that outputs your message is part of the platform, and it's also the platform where you find the configuration for instance, on KVM x86, if you want to see your message on a VGA output, or on a serial console, or on both, or nothing. And each platform has its own properties or devices where messages can go to. So to look where the output is going to, you should configure your platform. And then also one thing I should say, because this is still poor man or printf debugging, it is of course expensive, and it impacts your runtime. So we have also other tools for more performance critical debugging, but for, let's say, quick checking or deterministic behavior or something like that, it's often a good tool of choice. So how can you compile in and compile out messages? So this works a bit differently between kernel and debug messages. For kernel messages, we have this menu configuration called kernel message level, where you can individually enable, if you want to see all the information messages, or just warnings and errors and so forth. The debug messages, this is more intended for developers. So we have multiple options here. We have one option that we can globally enable all debug messages that are part of the code base. And this you find a sub option under the UKDebug library called enable debug messages globally. It depends how useful it is. Sometimes it's useful if you don't know what the bug is that you're looking into. But everything is printing, really everything. So it really blows your terminal. And if you're developing one piece of code, you probably don't want to see everything. So that's why we have two more options. So the second option, you can limit the focus of enabling debug messages by modifying your makefile UK of your library. For instance, you can with a compile flag enable it just for single source files. So you can distribute the compile flag to single source files, or you can enable all debug messages of your library with a compile flag that is then applicable for the whole scope of your library, for all source files in there. And the third option is, if you anyway have the source code open, you can also quickly define the macro UK_debug before the UK/print.h header is included. And then all debug messages in that source file, when it's compiled next time, will be enabled. So let me briefly show you how this looks actually in action, in case you didn't see it before. So, of course, in that, let's say, really parts of this source file, I need to include the UK print header first. Let's print a hello world debug message. As you see, I define the UK debug macro, so I choose option C to enable that debug messages. And on the right side, you see what is then coming up on the terminal. You have functions for printing kernel messages on all these different levels, like info, warning, error, and critical. So as further we go down, as more critical it gets, so as more serious the message is. The format of how such a message is shown is actually configurable, because we actually don't just print hello world, we print also timestamp, the level, the library where the message is coming from, the source file and line where the message is emitted from. But this is totally configurable. But you can already get a notion that this is really developer friendly, because by just seeing the console output, you can refer that back to which location the code, the message is coming from. Especially if it's an error message or something, you know exactly, I need to go into that library, open that source file, and then I know where I am. But it's configurable, so you can also hide some of these columns. And to give you an comparison to the standard printf, which we also can do, right? So we have also standard IO, we have standard out, standard error. So we can just do a printf hello world, but we will see only hello world. We don't know where this is coming from. We don't have instrumentation from the menu to compile out the message or not. So this would need to be done completely by your own. That's why it makes sense kind of using the print system for library state and so forth, and leaving standard out and standard error more for the application where it's really not important where the message is coming from. Additionally, we have some nice extras in libUKDebug regarding printing. We have a print function which is mimicking Hexdump. So it has roughly the same work principle as the UK print function that you just saw. Like you can print one, you can print info. So they also compiled in only or based actually on the configuration that you can do for the kernel and debug messages. The nice thing about Hexdump is because you often come into the situation that you just want to dump from a memory area the content of it because you want to check something, is that this is totally there. You just hand over the pointer of your memory object, the size of it, and some format arguments for the output. Or actually, if it needs to be really quick, we have even a shorthand where you just hand over the starting address and the size, and you get an Hexdump -c like output. So the people under you that use Linux or BSD a lot and use Hexdump -c a lot, I think they know what I mean with it. A second nice feature we have here is we have also a disassembler or access to a disassembler when we include an external library. The one that we currently support is libstudis. So I gave you here some links where you can look it up. But it also provides you through libUKDebug a same style of function like Hexdump, where you point to the starting address and then you tell how many instructions should be printed. And also here we have the full instrumentation if the function is compiled in or completely removed from the code, depending on the level, if it's a kernel message or if it's a debug message. So let's give you a short example for Hexdump, how that looks like, because that's sometimes really handy to have. So imagine we have a character buffer here with that hello world string again. If I use, should be getting really fast, if I should use the Hexdump -c like version, this is UK_Hexdump C, and then K because I wanted to print this on the kernel as a kernel message. I have to hand over there the level of that kernel message, then just the buffer and the size of it, and the output you see below. So which is totally in line with what you see normally with Hexdump. So you see the starting address and then the bytes, and on the right side, the column with the ASCII output. The, let's say, a bit more customizable column would be UK_Hexdump K, where you get these two extra arguments where you can format your output. So here I chose, for instance, that I still want to see an ASCII column, but I wanted to have the grouping of bytes. Instead of 8 bytes together, I wanted to have 4 bytes together, and I want to see in total just 8 bytes per line instead of 16 as the Hexdump -c output is. Okay, let's go to the next topic, which are assertions. We have also 2 types of assertions. I think it's a quite common concept. So people that used assertions before should be quite familiar. We have the same thing in Unikraft. And we have 2 types. We have runtime assertions, which are executed at runtime, and we have compile time assertions, which are checked at compile time. So let's talk first about runtime assertions. When do you use them? Actually, we use them mostly for checking for programming mistakes or API misuses, right? Whenever we define an API and we have a description, how it should work, which arguments you should hand over, we have kind of a standard. And with assertions, we can, for instance, check that the arguments that I handed over are complying with the standard. For instance, null pointer as an argument, although you didn't expect it, you can do that with an assertion. The second thing is you usually place some assertions in your code to still check if your system is in a defined and stable state. For instance, we found bugs already with this in the memory allocator code, for instance, because something was overwritten, and then we had a really weird state, but this was easy to catch thanks to in-place assertion. Assertion themselves, they're implemented with an if condition, and if that condition is not met, it prints a critical message also with the condition inside and crashes the system, because now we know we are not in a stable state anymore and we crash. Also, those can be compiled in and compiled out depending on a menu configuration. But in general, our recommendation is that for developing and debugging purposes, you should have assertions always compiled in, because they're kind of your friends. Develop something to an API somebody else was providing. But of course, because we have an if condition, there's some CPU cycles actually wasted. And when you're sure that your code is safe, weird states can't happen, which you can never promise, but you know what I mean. For production builds that really require high performance, you can of course let the build system completely remove all assertions from your code and get back performance. This actually happens for us with the TCP IP stack, which has a lot of assertions to check that the stack is still in a stable state when you parse a protocol or these kind of things. But they obviously, because the amount of assertions you have, they hit you in performance. Okay, let's do another example for how the Unikraft assertions look like. So imagine we have a function called gimme5, and the parameter is hand, and we do here an argument check. So in our specification, we specified that the integer hand needs to be 5, because gimme5 only works when you also give a 5 to it. So we can use an assertion here. And then as another use case to see if your system is still in a stable state, let's say, we could, here in our main function, after we called gimme5, we can check if a 5 was actually returned, because we expected that from our specification. And you see here also another thing. I used here UKBugOn, which is actually the same macro, but the condition in there is just negated. So meaning if that condition is met, then we have a bug. I could have used also UK assert there. And then I would write, instead of return unequal 5, I would write UK assert return equal 5, right? Because this is what I want to make sure. But it's just to show you have both options, and they behave exactly the same. Okay, compile time assertions. Those are actually not part of libUKB debug. They are in general available because they don't crash your system. They actually fail already while compile time, so we don't need a lot of support for implementing that. So we can treat them as a really basic primitive. And you usually use them to check, for instance, that configurations are validly set. They will always stay in the code. We don't have an option to compile them out. But why would we? Because they're anyway checked at compile time, and we have no overhead of them during runtime. So there is no performance difference if they're compiled in or compiled out. Let's give you another example so that they have a better imagination of such a use case. Let's say I have here this character array called my container, and its size it's retrieving from a menu config. So it has here config underscore my container underscore size. And then I have a function which packages something into that container, and the content is an integer. And what we do, our operation, what we do in there is we just mem copy the content into the container and use the size, of course, of the content, which is the size of an int. Now, what could go wrong? Actually, what could go wrong is that config my container size is smaller than a size of an integer, which could be 4 bytes, and config my container could be 1 byte configured. And then we have a problem because we're exceeding the bounds here. So for that, we could, for instance, use the compile time assert and can make use of the size of operation, which is then available by the compiler while it compiles, because it replaces it to static constants. And then this would fail, and then the compilation would fail as well. Okay, next topic. I'm running through all these points now. GDB. The interesting part of GDB is actually that many hypervisors, so if you imagine you run Unikraft on a hypervisor, which is actually most of the use cases, they provide you an GDB server interface where you can attach a GDB client to it. And the good thing about Unikraft is that it is a single address space guest. So debugging it feels really more like debugging a user space program, not like a complicated or more, say if you take a Linux kernel, you have the different address spaces, you have or privilege levels also. User space, and then swapping is one. So it really feels like a user space program. So how to do GDB debugging? First of all, you need to be making sure that you have a so-called debug file of your built unikernel that is also carrying all the symbols of your unikernel that the debugger can use to know at which addresses which functions and so forth. So to get that, you need to open the menu configuration, go under build options, debug information level, and then we recommend to choose level 3, which is the highest level, so that we have all debugging information in that debug file. The build system will still produce another image type which strips out all debugging information. So you could, for instance, ship the stripped file into production and keep the debugging internally, or doing your at your testing or debugging team that then can debug a production kernel as well. Then you execute the guest with the debugger server enabled, or what it actually will do is open normally a TCP port or a socket where you can attach GDB to. In our case, you can, for instance, use Craft, QEMU-guest, Zen-guest, or even do it yourself by using QEMU system directly. Or if you're on Zen, you can use XL, and then what you need on Zen is the GDB SX, which is the GDB server for Zen. Right. And the guest doesn't need to be run with a debug file, so you can just use the production image. And the debug file is only actually required for GDB when you attach it, because it loads all the symbols from it. And as soon as you're attached, you can debug as usual. And this is actually the common way you debug with GDB on all platforms. Although we have some specialty here, for instance, on QEMU, KVM on x86, this is a bit of a workaround, because what happens here is that during boot, there's a CPU mode switch happening. So QEMU will leave us the CPU in 32-bit mode, and we have early assembly code in Unikraft that switches that CPU in 64-bit mode. And when you attach the debugger while you're still in 32-bit mode, then GDB is not able to understand that there was a mode switch and then switch its internal representation of the remote architecture as well. So you need to do that manually. So this is really a special case here for KVM with QEMU. So how do you do it? First of all, you run your guest in pause state so that it doesn't execute when you instantiate it. Then you should have the debugger port open, so you can attach your debugger. set a hardware breakpoint to the first C code that we have, which is then in 64-bit mode. And this is in the KVM platform. This is libkvmplat entry. And we do a hardware breakpoint because those survive the CPU mode switch with the GDB backend. Then we execute and need then to disconnect as soon that breakpoint is reached, to disconnect the GDB. Set the GDB machine architecture also to x86-64 so that we are in line with the remote target again, and then we reconnect. And then from that point on, you can use all the features you're used to with GDB, meaning watch points, breakpoints, stepwise going through reading CPU registers and so forth. In practice, to show you how that really looks like when you type it, first of all, starting the guest and post state here with Kimo guest or with Craft, you have this option here to open the debugger port. This is this -G1234. This is our port we're waiting for, and then this -P will instantiate the guest, but it will not execute it yet. So it's just kind of a shell that is ready for execution, but it is stopping at the starting point. And then on the second terminal, you can start GDB. You load GDB with the symbols from the debug file. Then you connect GDB to it, to the guest, set the hard breakpoint, let the guest run until it reaches that, so it does the CPU mode switch. Then you disconnect, change the architecture, reconnect. And then you're able to do whatever you want to do to debug, like watch point, breakpoints, continue, stepwise continue, backtrace, whatever. Okay, trace points. So the thing is, so far, if you have only GDB and printf, it's a bit difficult sometimes in some scenarios to look into things that are really performance critical or really harm a bit of, because they harm the performance so much, harm the runtime properties. This is especially, let's say, if you do things with the virtual file system or with the TCP/IP stack. And for that purpose, we have, similar to the Linux kernel, trace points, which the idea is that you can observe events. So you can also instrument your code and observe when trace points are crossed, but with as minimal overhead as possible, and can analyze your data later at runtime. So this works by writing, actually first instrumenting your code. This is the paper sheet here on the left side. This should be the code sequence with trace points. So you place them in your code with things that you want to observe. And our trace point system has an in-memory trace buffer that writes while you're executing and crossing those trace points, the data into this trace buffer. When you're done with that, either your guest is now shut down or in a state where it sleeps, you can attach the debugger, or you had it even attached before, but you stop the guest now. We have some tools that makes it quite easy, actually, to access that trace buffer from GDB and read that output. And in this example, I'm not sure if you can read it, but here you see some records of trace VFS dub3 and trace VFS dub3, which were instrumented in the VFS core library, which is our virtual file system library. So, how do you define trace points? You have provided by the Unikraft system, or actually by libukdebug, a macro called uqtracepoint. And your arguments is first the function name for the trace point, a print format, and then the types of extra data that you want to add. The print format is actually just for formalizing later a message when you're reading and passing the trace buffer. What it will write down is just the string and the types itself, but all the string operation to do a nice format will happen offline. As here in this example, of course, I need to include the tracing header, which is provided by libukdebug. And then I define the trace point called here trace VFS open. And what interests me is the path of the file that was open, the flags, which is usually an integer, which I want to see as a hex print, and the mode that the user requested. And when I have that trace point, it creates me that trace VFS open function. I can just place it in my code where I want to have it. And when you enable trace points, this will cause an entry on the trace buffer of that event. So now how do you compile in and compile out trace points? Because our idea is always you should be able to keep the instrumentation of the code while compiling everything out so that nothing gets harmed. And if you're really interested in something, that you can just make use of the existing instrumentation. So for compiling in general, one option needs to be set, which is enable trace points in general. This enables actually the code for the trace buffer and is also reserving memory in your unikernel for saving the traces. Then you have multiple options again, and this is really close actually to what you have seen with UKDebug on where you want to enable the trace points explicitly. So A, and this is exactly the same as in UKDebug, you have an option, the menu option that enables all trace points wherever they are in the code base. So this could be, in all libraries, could be some trace points, and then this buffer gets bloated. But because of the same reasons, maybe you're still interested only in a subset of trace points or in the library that you're currently actually looking into. So you can do the same trick here. You can either modify the makefile UK to enable trace points per file or per number of files or for a whole library. Or if you have the source anyway open, you can also here define UK_debug_trace just before UK trace is included. And that is the same behavior as the debug messages. When you have that instrumented, you want to be able to read and extract trace points. For that purpose, we have actually a script provided which gets generated when you compile your unikernel, and it is placed under the build directory, and it's called uk-gdb.py, and that needs to be loaded by your GDB debugger. So you can, for instance, add that to your GDB init file in your home directory so that it gets loaded, but you can also type that later by hand, and then it gets loaded then. Then you get, with that, some extra commands available on the GDB shell. And having this, you're now able to attach GDB to your guest. One hint is, if you do, let's say, a benchmark or some other evaluation during runtime of the unikernel, and you want to probably shut it down and then access the trace buffer, obviously you need to make sure that the VM is not destroyed so that we still have access to the trace buffer. Luckily, the schema guest -G option that opens a debugger port is implementing that behavior, but you need to make sure if you use some other tool to instantiate your guest, that you have this option that it stays alive. So reading the trace buffer is as simple as just typing UK space trace, and you can also save a copy of the trace buffer with UK trace save and then an output file. And there's another tool which I didn't write down here, which you can use then also then parse that saved file later, so that you still get the same output as UK trace does it while you're in the GDB session. Okay, now I want to give you an outlook of more tools for debugging, benchmarking, and profiling that we're working on, and which we hope many of them will appear soon in Unikraft upstream. First of all, is we're heavily working on unit tests. This is a system to repeatedly test APIs and implementations that they behave correct. And the idea is that you keep those tests, and if you enable them so that they compile in, you can check that your modifications of code is not breaking any of these tests, which are obviously testing the specifications of APIs. The syntax that we have chosen is closely inspired by KUnit, which is the unit testing framework that the Linux kernel folks also use. The other item that is coming up is an Unikraft internal GDB server, so that, let's say, on platforms that don't have this GDB server support, which happens, for instance, on Hyper-V, or whenever you run Unikraft on a bare metal node, meaning without any virtualization, let's say you run it directly on a Raspberry Pi, it's a bit hard to debug. And with an Unikraft internal GDB server, you can directly communicate with Unikraft and over a serial connection and attach the GDB to that. And the other advantage is that in that implementation, it's also much easier for us to also enter the debugger as soon as an assertion failed, or when a crash happens, or a trap was called, right, by division by 0, or a page wasn't mapped. This is much easier to do with such an implementation than you needing to set up breakpoints on the page handler or on the assertions that you're looking for. Another nice tool regarding performance analysis is Uniprof. This is a tool that is based actually on a high frequency snapshot of your stack, or actually the backtrace of your stack, so that you know which function nesting was happening. And you can visualize those samples with a flame graph, which was some years ago was actually becoming a bit more popular through Brandon Gregg. But it is a really nice way to understand which functions take significant amount of time on your CPU, and they quickly point out where you should optimize something. But that's not all. We have even more projects running, like Kzen, which is similar to Linux, a kernel address sanitizer for Unikraft, so that we also get the functionality to detect use after free or out of bounds errors that can happen with allocations. And another nice thing that we're also working on is on profile guided optimizations with GCC, where you give the compiler the chance to produce optimal code for your use case. And that roughly works by first instrumenting a first build of the unikernel through the compiler. And then second, you run that instrumented compiler with your workload, and that generates actually a profile file. And this profile file you give in a third step a second time to a compiler, or to the compiler, to actually do the right optimizations with loop unrolling, branches, and so forth, depending on the profile it collected. Okay, that's it. That was my talk. I wish you very fun with the hackathon, especially the session about debugging. And I hope that this overview is already helpful for all these tasks you're going to do, and also the ones that are not, just playing around with debugger, but also the other tasks where you actually have your first bug with Unikraft and debugging. So,
all right. Thank you so much, Simon, for this. There was a question that I answered from Dorin. Dorin, I hope it clears things up for you. So that port that we use for GDB is actually a port opened up by QEMU. So QEMU opens a GDB server, and via that GDB server, you are then able to debug a remote target.
Yeah, exactly. That's right. Yeah, that's integrated in Kimo, and then I was mentioning there's an extra executable that has the hypervisor, which is called GDBSX. That's the same for the hypervisor.
Yeah. Okay, so kind of summarizing, you have all those options that are available in Unikraft. We're going to go through a bit of those, especially GDB and trace points, and well, the UK debug interface on this session. And then we're going to continue with the others. Bear in mind, these are very important topics, both with respect to kind of debugging, getting to know what's happening, and then, as Simon put it, a way of improving the performance. This would be it from my point. If there are any questions, let's wait 1 or 2 minutes to see if there are questions from your side, and if not, we can close this and we can move to the USoC channel. So if there are any other questions or remarks from your side, this is the time for it, please.
I have only a small question. Will we find the presentation somewhere here in Discord?
You can put the presentation on the USoC website, maybe?
Yeah, good.
Yeah, also eventually, it'd be nice to have this on the documentation website. But as a reminder that this talk was recorded and will be on YouTube.
But also, what I hear about it's mostly extras documents and the docs.unikraft.org. There's a special section about debugging, especially how to attach GDB and also the weird fixes for Kimo KVM on x86. This was documented. Also, the trace points as well.
Is it my connection? But Simon, you're breaking up a lot.
Yeah, it's. I thought it was on my side.
Sorry.
So I think, Simon, that the thing is that this set of slides kind of are very compact and grab everything in one place. So that's kind of the idea of if people would have access to them. If not, they can still look at the video that we recorded.
Yeah, but no problem to give access.
Awesome.
Right. We'll put it on the official documentation website then.
Okay.
Under resources.
All right. So